Hi, I'm Orman Debbie, an assistant professor with the Department of Mechanical and Mechatronics Engineering of Southern Illinois University at Wardsville, and you're watching the presentation for consensus of incommensurate order fractional multi-agent system with a fixed length memory. The general layout of this presentation, I will start with some history of the fractional calculus and basic definition in the fractional calculus and the importance of them in some engineering applications. And then we will talk about the consensus problem of the fractional multi-agent system with the fixed length memory and the buffer overflow issue with them. And we are proposing a method, and we will talk about the methodology and idea behind of that method. And we will show the advantage of that method in an illustrative example. So you might think that the fractional calculus is a new topic. Indeed, the born of the fractional calculus is going back to 1695, when the Leibniz was proposing the Leibniz rule. And that time, it was asked by L'Hopital that what would be the meaning of the half differentiation of the function. Leibniz replied, it leads to a paradox from which one day useful consequences will be drawn, and he was not far from this statement. After a century, there were many applications, especially the Abel's integral, or Abel's actually problems that could be solved in the framework of the fractional calculus. How we are defining the fractional operator. So let's start with the idea of having n-fold Cauchy integral for a function. So the nth integral of a function will be described by n-fold Cauchy's integral, which is going to be explicitly formed in this expression. We have these factorial operators where we can just replace this n with a fraction and replace the factorial operators with the twins gamma function. And we ended up to having the alpha's integral of the function. This is known as a Riemann-Liouville fractional integral. In this definition, we are going to have an arbitrary lower terminal, or number a, which is indicating the memory of the process. The left-sided Caputo derivative is known as the most known fractional derivative operator, and it is defined by pre-multiplying the integer derivative by a fractional order integral. And the good thing about this definition is that we will have some nice properties, including the property that I am actually showing here in this slide, which will be used later on to develop our method. And this property, you can see that the fractional derivative of the power function, such as t minus a, if the a is going to match to the lower terminal, it can be explicitly expressed by the simple power function that we have in the right-hand side of the equation. Next, you might ask that where we are using these fractional operators. Well, these fractional operators can appear in the governing equation of a process, or a dynamical actually process, and coming from the nature of the physics, such as the Abel's integral that we have for some of the problems, or non-Fichtean diffusion. As you see in this problem, this integral has a singular actually kernel, which is going to be nothing more than the fractional derivative operators. Or the non-Fichtean diffusion, we can show that eventually we ended up to having fractional derivative operators in the sense of the Riemann-Liouville. Or you might use this fractional operator as a tool in the modeling and try to get a better response and higher performance compared to the traditional model that you have. As an example of that, if you have a system that has a memory and you would like to capture the memory, you can actually use this fractional operators, or in your controller. So you might use this orders as extra parameters to tune the system. Speaking of this chart, I would like to show you a couple of more examples here. So the first example is going to be Abel's throwing a stone in a potential field. So if you are trying to, in this problem, we are trying to determine the trajectory of this particle. And we're just simply using the laws that we have for this problem, the laws that we have for the physics of this problem. And we ended up to having the trajectory expression by this equation that has been highlighted. As you see in this green box, this integral is nothing more than the fractional derivative of the function, which can be resolved in the framework of the fractional calculus. In the second problem, you can see that the Volterra suggestion to capture the hereditary property of the population models by this convolution integral with a singular kernel term. So in the fractional calculus standard textbook, you can see this is nothing more than some fractional operators. And two more problems that I deal with them recently. So the first one is modeling the creep behavior of the epoxy. And as you see in this picture, the black line is showing the experimental data, and we would like to use some system identification and using the transfer function. And if you just use this transfer function, you can just see that your response is going to be far away from the experimental data. But just adding a simple fractional term in the transfer function, it is going to give us a better response compared to the previous one. Or you can use the fractional operator and these two parameters in your controller and try to get a unique response from this fractional PID controller. It should be noted that using these two parameters is going to be equivalent to using an infinite number of the parameters in your classic control, and you would not get the desired response, the same response, by just using a finite number of parameters in your classic control. Okay, getting back to our original problem, to basically model the information exchange between these agents, we can just use the graph topology. And for that purpose, we are only using a Differentiation Matrix, and there are more details has been provided in the paper. This is the general equation that is describing the dynamics between these agents as equation number 3. And we are trying to define this U, which is going to be a protocol for us, to reach to an agreement between all these actually agents. We are choosing this controller purposely as a PD type, but with a fractional derivative, as it shows in equation number 4. Since the beta is not going to be equal to alpha, and there's no relation between alpha and beta, we call this the system as a incommensurate system. And to make it more practical, we are trying to shorten the memory that we have. So that means that instead of having this fixed length terminal, we let this actually become varying and shorten at the time to the length of tau. We eventually ended up to having the equation number 5 that we need to find this Kp and Kd and beta such that stabilize this actually system. So for now, there is no method to be able to actually stabilize the system, including this incommensurate part, and also considering this shortened memory for that. And we are proposing that for the first time. What is the idea and how our method works? Well, the idea is that we would like to approximate a state transition operator. So this is different from the state transition matrix. And the state transition operator is going to actually map the solution from one domain to another one. And this is different from a state transition matrix, which is going point by point. Now we are going domain by domain. If we prove that this state transition operator is going to be same for jumping from one domain to another one, then we can replace that with the monogeometry operator and say that the solution from one domain to another one, or from the initial condition to the solution in the nth domain, it will be related to this monogeometry operator to the power j, and therefore the stability of the system is related to the spectral radius of this monogeometry operator. But how we can approximate that monogeometry operator? Well, we are using advantage of using this orthogonal polynomial by considering the solution are going to be a square integrable function. And the polynomial we're choosing is a shifted Chebyshev polynomial, which is going to give us the best approximation under the maximum norm. This is a general form of the Chebyshev polynomial in the recurrence relation, as you see in equation 6, which are complete in the LW actually a space, which the W is going to be weight function. And therefore, any function can be approximated in the form of this equation 7. And taking advantage of this power function, the property they have for the fractional derivatives, we can just show that the Chebyshev polynomial can be approximated with the equation 8 with some coefficients of Cn and Bn, regardless of the choice of the function that we are approximating. And therefore, we can just implement the fractional operator, the derivative operator, at the approximation function that we have here, and try to build a differentiation matrix. This differentiation matrix, it is going to be constant regardless of the choice of the function. If we multiple the discretized value of the function at some collocation point by this differentiation matrix, it is going to give us the discretized value of the fractional derivative of that function at those points. To be able to discretize the whole solution, taking advantage of advantage of this differentiation matrix, we're using some discretization techniques that the full details has been provided in the paper, and we are omitting those in this presentation to save the time. But eventually we can show that the solution is going to be given by equation 11, where we're going to have some discretization operator. And this in this equation, we can show that the monodromy operator is going to be given by equation 13, which is including the Kp, Kd, and beta. And therefore, our control problem is going to be turned out to a nonlinear problem where we need to determine those coefficients such that the spectral radius of this monodromy operator locates inside of a unit circle. To show the advantage of that method, we consider the 6 actually multi-agents that they are defined by this Laplacian matrix, and also the dynamics is going to be governed as a fractional double integrator type, and we shorten the memory at the tau equal to 52nd. Without a controller, there is no agreement, and there is no consensus here. But if we choose the controller as a PD type, as we mentioned before, and following that idea that we would like to minimize the spectral radius of the monodromy matrix and force that inside of the unit circle, we can just show that using a nonlinear programming, all this spectral radius can be less than 1. And also the optimal value for them, it is necessary that the beta should be like free and not equal to 1. And that's one of the advantages of our method. Eventually, you can see that the solution, it is going to be actually reached to the consensus, and all these states, they are reaching to a same value over time. Okay, in summary, what we have done, we were trying to solve the consensus problem for multi-agent system with a fixed memory and in commensurate order controller or a protocol, and we showed that our proposed method works perfectly for that type of a case, and for the first time we can establish this type of a system. Thank you for watching this presentation, and I hope that I can answer some of your questions in the conference day.